My name is Luca, and together with Christos, I work at AdStart. AdStart is a diversity recruitment platform. What we do, we provide companies and big corporates with software as a service. Our platform allows them to manage candidates at scale, and we try to make that as painless as possible and as fair as possible. Part of what we do is providing recruiters with a measure of suitability that matches candidates to openings. You have to imagine this in the context of having 20, 30,000 applicants for 100 or 150 positions. Sometimes the task is so daunting that all those candidates get is a 1 second, 2 second look at their CV, which is actually very often biased by some preconception. Do you have that uni, or have you gone to that cool company for an internship? Yes, you know, this is the part of the people who got rejected, this is the part of the people who got accepted. Doing it with software allows us to go a little more in depth into those issues, trying to understand, well, let's look at your, I don't know, at your experience there, or that particular education, or maybe that online certificate. We can do a more holistic first stage screening in order to allow recruiters to focus their time in one-to-one interviews or committee interviews with the top 20% of candidates who actually have the credentials to go to work there and are aligned to the company culture. Now, of course, every time you do this, this involves machine learning. This involves deploying statistical models in production which are used to produce numbers which then support decisions. So it kind of falls under that scary label, which is in GDPR, that is called partially automated decision-making. And this is scary because sometimes people might disagree with your decision. So some candidates might say, I don't really think you judge me fairly. I really think that I'm the best for that position. But your score led the recruiter into thinking that I was not the best. So we need to be able, at any point in time, to go back and say, OK, let's open the box and let's see why you were judged as not suitable or not so suitable or less suitable than the other candidate. Which means that in a year or 2 years' time, I need to be able to go back to my models and ask them, OK, but what happened here? Which is why you can understand that this conference is very, very close to what we do and what we need, actually, because it directly hits our business bottom line. So let's take a step back and let's talk about machine learning in businesses. Machine learning in businesses usually happens in 2 different environments, which can be more or less communicating depending on what you do. The first environment is prototyping, in which all you care about is proving that a certain model or a certain task can be achieved. So proving, for instance, that you can concoct a fraud detection model which has a certain level of recall. It just doesn't matter that it's perfect or that it works in production or that it's robust. You just want to know, can this actually work? Is it worth investing 2, 3, 4 months into researching and developing this solution? And so all the focus is on functional requirements. Can we do this? Once that is achieved, then what you want to do is to move to production. So actually working on a solution which is functional actually can be deployed to users. And what's very important is live and is going to get and interact with people, which are not the people who designed it. Now, in production, of course, functional requirements are very important. So I want that accuracy to be on the same level that it was when I was training the model offline. I want that recall to be in the same range. But there's also a whole other set of requirements which becomes fundamental and that are often not treated as important as the metrics that machine learning models are judged upon. These I call operational requirements, and I'm going to list some of them which I believe are very relevant for machine learning in particular. The first one is robustness. So is the model capable of handling foreign data gracefully? Or does it produce nonsensical prediction as soon as you deviate from the distribution of the input data you trained it upon? Then you have availability. Is the model capable of handling how many requests per second? Can we actually deploy this thing in production? And can it be used in a setting that requires the response to come in, I don't know, half a second or a quarter of a second? Monitoring. Is the model and the whole pipeline, because you need to take it holistically, something that we can monitor when it's in production? Can I know if the model is up? First question. Can I know if the metrics that I measured offline are actually being upheld online, and there is any mechanism that I can use to say, whoa, something's going wrong, maybe you want to take a look at it. And then you have debugability and auditability. So if something goes wrong, can I actually fix it? Do I have enough information to identify and pin down where the problem is, what the problem is? And I like to think about auditability as simply being able to debug something at any point in time for a certain period of time. So a year ago, 2 years ago, 7 years ago, depending on the industry standards and requirements. Which, of course, leads us to the main topic of this event, which is reproducibility. If we want to have debugability and auditability, we need to be able to reproduce what we do. Now, I'm going to repeat something that all the other speakers said, but I didn't have the slides, so forgive me. What are the ingredients for reproducibility? The first two ones are very familiar to people who work in software engineering: code and environment. If I can reproduce the environment using Docker containers or whatever technology, I can reproduce the code that is versioned on GitHub, Mercurial, whatever you use. I usually can reproduce the behavioral software. Now, machine learning systems usually have one another ingredient, which is radioactive, which is data. Data is radioactive because it's very difficult to manage, and if you change the data, even if everything else remains the same, the results can change dramatically. Now, how do we handle this dangerous material? The first phase where usually you get to touch data in a machine learning task is training phase. Training phase has some input and some outputs. The input can be data that comes from a serialized data set, which is usually in different formats, in different places. It can be locally, it can be remotely, I don't know. Or, as it happens usually in company and businesses, you have databases. So your data comes from queries. And databases are global state. You're not the only one who owns that database, so you're not the only one who's touching it. They change over time, it gets complicated. And then that's the output. So what do you want to get from the training? Well, you want to get some models. These models are usually going to be serialized files, so those very ugly pickle files we were speaking about before, which are very sensitive to being deserialized exactly in the same environment they were trained upon. Then you will have transformers, so if you normalize your data, you have computed, I don't know, the mean and the standard deviation on some features. You want to be able to transform the data you're going to feed into the model at prediction time using exactly the same mean and the same variance. And also, I would add that on serialized models, you also want the metrics and the metadata to be stored. So I want to know that after that training, that model achieved this level of accuracy, which allows me at inference time, at inference time to actually say, okay, is it behaving correctly? Is there a big discrepancy between what I observed in the lab, so to speak, and what I observed in the actual real world? And actually, there will be much more things to add at inference time. Now, we're going to present a very practical use case. So we're going to present our skill recommendation system. Now, we'll actually do a forward to show you this. So this is what it looks like. When a person signs up on Start, we ask them to fill in information. We ask them to fill in a profile, which we want to represent them as better as possible, and we want it to be as comprehensive as possible. Now, a lot of the people we work with are graduates who apply to graduate schemes. And a lot of people who come out of uni, when you ask them, what are your skills, they get a blank face. They don't know what to tell you. And when you have an empty page which says skills, enter input, they're paralyzed. They don't know what to enter. And so they go for the communication, teamwork, I don't know anything else. So what you want to have is a system that allows them actually to enter as much as possible. So the first thing we do is we break it down in different sections to make them reflect, okay, there are soft skills, then there might be some industrial skills. And the second thing we want is, okay, enter what you believe you know best, and then we might suggest you something that maybe you don't think is relevant. But actually, we know that your employer might care if you list that among your skills. So, I don't know, PHP, jQuery. And of course, this suggestion needs to be relevant to what you've entered. Otherwise, it feels a bit weird. So, we wanted to deploy this skill recommendation system. And we did it this way. So, the input is a table, which is the skills that every user has, is at least a table of IDs. And the output is a very simple SVD model, so nothing very fancy. There is some fancy stuff to make it optimize at inference time, but that doesn't matter. And a certain number of transformers, which are used to decouple skills, because a lot of people do spelling mistakes, Or you might be amazed by the number of ways you can spell Microsoft Word when you enter something into a skill form. That is very painful. And we also want two other things. The first thing is, all of this, of course, lives on Git. So this is code in a Git repository. What I want is, every time a data scientist, in this case me, pushes a change to Git because I'm fixing a bug, or I'm changing a parameter because the parameters are in this GitHub repository, I want immediately to service the updated model to production. So I want that Git push triggers a new training phase, a new evaluation phase. The serialized model goes in a magic place that Christos is going to tell you about, and then it's going to pop up in production. This is what I want. And I also want to do automated retraining. So when you do recommendation systems, it might happen that the distribution of the input data changes over time. So for instance, we might have had on our platform a certain number of roles over the years, and these roles have attracted people with a certain background and a certain amount of skills. Now, tomorrow we might close a new contract in a new industry, and the people who come to our platform have different skills. And those skills are not in the data set that model has been trained upon. So they're going to get nonsensical suggestions. This is unavoidable, but we want to make that unavoidable for a very short amount of time. So we want, as soon as we know that the distribution is shifting, I want to retrain it. So the simplest way to do this is retrain on a schedule. Every day, every 6 hours, every 12 hours, as frequently as I deem it necessary, I retrain the model from scratches. And I need to know that the model that was retrained, even if the code was exactly the same, is not the same model. There are two different models, and I need to be able to know this as different versions. Where do I store those versions? How do I do that? And this comes as a general comment on data science culture. So data scientist is a very indefinite figure, but in the mindset of a lot of people, especially if you read the job descriptions for positions, they're kind of statisticians thrown into industry. And they get this very lab feeling of, I do all the science and the cool stuff, and then I hand all this weird package to someone who's going to make it work in production. Which is, as we were discussing yesterday at dinner with the other speakers, where software development was 10 years ago. Now, the funny stuff is the software development has gone through a growth process to grow out of this, and that has been DevOps. We need something similar for data scientists. Do we want to call it DevOps? Maybe yes, maybe not. What we want is data scientists to take ownership of everything they do, and the boundary of that ownership needs to be as close to production as possible. They need to be able to prototype, deploy, and manage what they have deployed in production. You did it, it's your responsibility. But to do so, they need skills and they need tools. Some of these tools are not available right now, which is why this is a two-people talk, because I said, well, let's do this, it's cool. And I said, I'm not really able to do it. I need some help. That's where Christos comes in. So tooling will come, but the culture needs to change first, because those people need to reach for those tools, and they need to know that it's important for them to actually do so, because otherwise their job is going to be impacted. The value of what they do is going to be less, because what they do is not reproducible, it's going to break in production, they will not know why. If you have a fraud detection system and it breaks in production, and every single bank transaction is labeled as fraud, it's a massive fuck up. And someone is going to come to you and say, what happened? And you will not have an answer, because you don't know how that happened, because you can't reproduce it. So what needs to be said in the business environment, different from academia, is that reproducibility has a price on it. And it delivers value which is economically measurable, which is why companies need to care. Now we'll let the stage to Christos, which will show you some funny stuff.
Hi everyone, can you hear me okay? So I'm Christos, and I work at HeadStart as a DevOps engineer as well as a full stack developer. So what I do and what I've been doing in the last year and a half that I've been there involves a lot setting up infrastructure, setting up automation and pipelines to enable our teams to basically deploy things to production faster, to make sure that everything is safe and that everything can scale as the business requirements change over time. So what I'm going to do today is I'm going to talk through a little bit the solution that we came up with to take the idea that was the skill recommendation engine from a prototype and put it into production. What was required in order to do that, and what tools are we actually using to achieve this? So let's get into it. many moons ago, I had a meeting with Luca, which went along the lines of, we've built the skill recommendation engine, and it's ready to go into production. And basically, my reaction to this was something along these lines. And we started listing the requirements which were not yet fulfilled in order to really take this to production and make sure that it works with our current user base. And this is the list of things that I'm going to talk about today. So the first thing on the list is something that's been covered a lot today in all the talks, and it goes back to controlling your environment and having strict dependency management. This means that any packages, external libraries, data, even the environment that you run in need to be reproducible. Basically, it goes back to avoiding the "it works on my machine" situation, which is a DevOps nightmare. Next is model performance analysis. So we need a way to automatically, when we train a new model, assess, is that model suitable? Does it perform as we expect? Is it as good as previous models that we've trained? And ideally, is it better than previous models that we've trained? Because we want to improve over time. Next, I'm going to talk a bit about how we do model versioning. Obviously, this goes back strongly to reproducibility and auditability. We want to know exactly which piece of code produced that model so we can repeat that process. And then I'm going to talk a little bit about infrastructure and how we manage infrastructure. So how do we have confidence that the infrastructure that we use on the cloud is going to be able to handle the current amount of requests, the current amount of users that we have, as well as give us the confidence that it can scale to handle traffic in the future as we grow as a business? How can we be sure that it's reliable, it's stable, and it's always available when we need it, so we don't get random errors being thrown left, right, and center, and getting woken up on the weekend and having to come in and solve these problems? And also, how can this be managed in a sane way? A lot of the things that have been said in the previous talks about clicking things in GUIs and setting up stuff, it's not reproducible. It's not easy to document that workflow. So how can we avoid that when setting up infrastructure, where a lot of the cloud providers now have very good web consoles where you can go in and do everything from your web browser? Then I'm going to talk a little bit about data versioning. How can we make sure that the second side of reproducing a model output is versioned as well? How can we know what data was used with this model, and why did it give a certain output? And finally, I'm going to tie everything together and talk about our continuous integration and delivery pipeline, which incorporates all of these things together to take us from a code change to a live model in production. And just on that note as well, continuous integration and delivery really isn't just about the tools. It's about a mindset, and it needs to be embodied, which is why I kind of hate saying that I'm a DevOps engineer, because DevOps should not be a profession. It's more about a mindset, and everybody in a professional software data science team should embody that and try and think about how can their changes be safe to be taken into a production environment. So, what do we use for dependency management? Our skill recommendation engine that we've built is using Python. And the Python package management world is a fun little world, which I recently got into. And a tool that we use to manage this is called pipenv. Has anyone heard of pipenv? Yeah, fantastic tool. They advertise themselves as Python development workflow for humans. As much as I like to think that I'm becoming one with the machine sometimes when I'm doing my DevOps work, at the end of the day, I'm still human, and I need to maintain sanity at the end of the day. So a tool like this is really great. Essentially what it does is it manages virtual env for you, and it creates a log file which pins down the exact version of all the packages that you're using in your code base, so that the next person who comes along and tries to install those packages is guaranteed to have the exact same versions. This is also really valuable for going into production, because let's say an open source tool accidentally introduces a bug and you end up installing that new version in production and it breaks. that's not a good thing. So you want to be very in control of when you update package dependencies. And the other tool that we use is Docker, which has been mentioned already a lot today, but I'm going to go over it again briefly. It's all about reproducible environments. How can I make sure that what I run in production is going to be exactly the same as what I can create locally, which at the end of the day reduces the amount of crashes, failures, and bugs that we will have. So, model performance analysis. Essentially, we have two main questions that we want to answer when we create a new model. And the first is, standalone, does the model meet basic performance requirements? If we run some performance analysis on it, do the metrics that that performance analysis show us meet a certain base threshold that we decide beforehand? And then the other step is, if we compare it to a previous model that we've generated, how does it compare to that? Is it better? Is it worse? Is it within an acceptable range of behavior? And when we make these performance analyses, we also need to store these alongside of our models. What this allows us to do is to go back in the future and generate analytics of the performance of our model over time and see, are we improving things? Are things getting better over time? And if not, why? Onto model versioning. There's really two levels of versioning that we have. And the first one is related to the code which produced this model. So if we create a new version of the skill recommendation system and we tag it version 2.0 on Git, we want to associate the model with that version. So we'll save this tag alongside our model. And then the second step is to understand which data produced this model. So because we're automatically retraining the model and the data is changing over time as we have new users, we essentially have models which are on the same code version but with different data versions. So we need to store that information as well. And this was mentioned earlier, but we use Amazon S3 to achieve this. So we store our models in S3 bucket under folders with the tag which matches the code version. And inside there, we have an object which is version. So when we create a new model, instead of simply overwriting the previous one, we create a new version. And we can go back to any version that we like at any time. Now, this is very important for reproducibility, but also for being able to roll back in situations where we deploy a model and we realize that it's degrading performance in production, we're having problems. We can very easily switch to a previous version and restore that problem. Let's talk about infrastructure. I mentioned some of these points earlier about needing to be able to scale our infrastructure. So in a world where you have Docker containers, this becomes infinitely more easy to manage. You can have a set of machines, a set of instances on AWS, for example, which work as a cluster, and you can say, I'm going to deploy 3 Docker containers in this cluster. As demands change, you can scale those containers and those number of machines automatically based on a certain metric. In our case, the skill recommendation system is very CPU bound. So we can look at the CPU usage of the cluster and see when it goes above a certain threshold, we want to increase the number of containers, increase the number of instances to match the demand in production. And AWS has lots of tools which enable this. The other thing is that infrastructure, just like code, needs to be maintainable and easy to expand upon or upgrade. And in most businesses, it's very important that you can reproduce a similar infrastructure in various environments. So usually, most companies will have, for example, a staging environment, which is an environment where you deploy your changes first, test that everything works, and it's similar to the production environment before then moving on to really deploying into production. And what you don't want to do is spend hours setting up your infrastructure in staging and then say, yeah, it's okay, and then have to do all that process again in your production environment. So how can you achieve all of this when traditionally infrastructure is quite a manual management process? We use a tool called Terraform. Does anyone use Terraform here? I think it's an amazing tool, and before I had heard about it, everything was kind of a mess, to be completely honest. Terraform essentially is a tool that lets you write your infrastructure as code. So they've created a library where you're able to describe what your infrastructure is in a code format. And using some simple commands, when you make a change to that code, Terraform can output a plan, which is essentially like a git diff. What it shows you is the difference between what you're currently running and what changes you want to introduce. You can look at that output and say, yeah, these are the changes I want to make, and apply that plan. And the other thing that comes with code is obviously reuse of code. So what you can do is you can create modules of infrastructure. Let's say I have a cluster and containers, as I talked about earlier. We can make that a reusable module and use it several times. So next time I need to set up an auto-scaling cluster of containers, I can just reuse that module with different parameters. Think of it like a function in normal code. This is a very powerful concept and has enabled us to, with very few developers and essentially just myself as a DevOps engineer at Head Start, to do amazing things in the cloud. And the other thing that it does is it enables other team members to develop infrastructure. Because everything is easily visible in GitHub and you can understand what the infrastructure is, it's easy to go in and make a small change. And this is part of the DevOps mantra, is trying to enable everybody in the team to be able to go out and make changes and deploy to production. So let's talk about how we do data versioning for our skill recommendation system. Now, the way that data is versioned depends very much on how that data set is originally created. And in our case, as Luca mentioned, it comes from a database query. So at the time of training, we do not only just query the database and use that result to train our model, but we also save that data as a snapshot, and we save that snapshot alongside the newly trained model, so that if we want to go back and reproduce it, we can do that very easily. I'm going to go on now to talk a little bit about continuous integration and the tool that we use at Head Start. But again, I want to reiterate that continuous integration and continuous delivery are not just about tools. They're really a mindset that everybody in your team needs to adopt in order for it to work as efficiently as possible. So assuming we're in an organization where that culture has been adopted, so developers are writing tests to make sure that the code which they deploy is working correctly. They are managing their dependencies in a way which is reproducible and ensures that it will work correctly in production. You need a tool which can automate all of these things and help with that process. So at Head Start, we're using CircleCI. CircleCI is a really great tool if you haven't heard of it, and it makes CI and CD quite simple. It's not the most configurable as something like Jenkins is, but it definitely saves you a lot of development time in making that process as easy as possible. So basically what CircleCI is used for is to create an environment or a pipeline which performs certain steps. The first step will always be to run automated tests. Make sure that the code that you're running doesn't break any tests that have been written previously. If those tests are passed and the code is merged into the main branch on GitHub, then you want to trigger a build which will create your models, your Docker containers, whatever you may need, and deploy those into a production environment. So let's go through a full flow of how a change in our code for the skill recommendation system reaches our production environment. So we have a GitHub repository called the Skill Recommender System. Essentially, this contains the code which is needed to train a new model. A change in this code is packaged and deployed to a private PyPI server so that we can access it from another code base. Then we have a second GitHub repository, and Luca has decided to make a change. So he pushes this code to GitHub, and assuming that all the automated tests pass, he'll merge it into the master branch, and this will trigger our CircleCI pipeline. So the first step in this pipeline is to build a Docker container which, when run, will output our new models. The second step, which is done outside of CircleCI, is to actually train those new models. The reason this is done outside is for performance reasons. So we trigger a server on AWS to run the previously built Docker container and output those new models somewhere where we can access them. The next step is to assess the performance of these models. So we first run a standard performance check. Then we also fetch the latest model from production and compare the two. Assuming that this passes certain standards, we then upload these models to Amazon S3. We have a system where our AWS environments are very segregated. So all of this is happening in a specific data science environment. But when we upload these models, we want them to be accessible from our web applications. So we're uploading them to a separate AWS environment, which is accessible from those web apps. Finally, we have another Docker container that we build, which is actually the API that runs, that serves requests. So it's a small Flask application, which essentially receives a set of skills from a user who's entered their skills and returns back some new recommendations. This Docker container is stored in a repository, which is then accessed and run by our, inside our production environment. Now, what I haven't touched upon here is how does the scheduled retraining of our models work. Essentially, it's the same thing, but a smaller subset of this pipeline. With CircleCI, we trigger scheduled builds, which happen several times per week for this system. And what will happen is it'll use the previously built container, since the code hasn't changed. It will train new models, again, assess their performance, and assuming that everything is as expected, performance-wise, it will upload those new models. And finally, instead of building a new container, because no code has changed again, we simply restart the running containers in production in a safe way. And yeah, that's the full flow of how we deliver new changes of the skill recommendation system to production. Now Luca's going to wrap this up with some improvements that can be made in the future.
Okay, so the first one is data versioning, right? So S3 is very nice, it's very functional. Every time you push new data to S3, you are actually pushing the old data again. And S3 is going to store all your data, one upon the other. But sometimes you are just changing a row, renaming a column, doing some cleaning here and there. You don't really want every time to upload 1 terabyte of the 1 terabyte data set to the cloud, because it might take time. It might be also painful. So we want some Git diff for data. We know that this depends on the format in which you save your data, and there might be dependencies, there might be complete technicalities to solve, but this tool does not exist right now. That's the first big problem. The second one is painful transition. So as I said before, the prototyping phase is very much free flow, freestyle. Do whatever you want, prove me that it works. And then when we go into production, it becomes the sanctified place in which everything needs to work, and we go TDD and continuous integration and continuous delivery. We want something that bridges that gap. So we want to pass from prototyping to production a little more smoothly without bringing in tools that completely change our prototyping workflow. We want something a little more soft that we can plug in without having to change everything, like Pachyderm or DVC. They're very invasive. So we feel that if we commit to use those, that it will be very difficult for us to pull out. And that's something we don't like. The third one is, of course, this needs to be generalized to an internal tool, because this will allow to reuse the whole concept and all the pieces that we have brought, mostly part of the infrastructure that Christos has brought, to do this orchestration of different models. Because if you have a data science team, usually we are 3 people right now, we have a model output which is pretty sustained. And it's not possible to have to go through all the designing of a new system when you want to deploy something to production. Ideally, this kind of workflow should be eased by another tool that we simply use to actually do this. So we have great expectation for .mesh when it reaches Python scripts. But for now, what we're probably going to do is to generalize this on internal tool. Eventually open source it, who knows. That's it for now. Thanks a lot.
Thank you.